So there's all these different ways of taking two functions and producing new functions. You could add, subtract, multiply, divide two functions. You can take two functions and compose them, meaning that the output for the one becomes the input for the other. In light of this, I'd encourage you just to pick up your pen and just write down some extraordinarily complicated functions. Right? The function that you write down has probably never been written down in the history of humankind. I mean, there's just so many different choices that you could make when you're combining all these different algebraic operations. And that's part of what makes calculus so amazing, right? There's just a huge variety of functions out there. But not every function really has its source in just combinations of algebraic symbols, right? A lot of the functions that we want to study are really functions that are somehow coming from the real world. So I want to see some real-world examples of functions right now. So here's one, unit conversion from Celsius to Fahrenheit. These are two different temperature scales. So the function will be f of x is 9 times x over 5 plus 32. So this is just a linear function. It's going to be a number times x plus a number. And let's take a look. What's f of 0? That'd be 9 times 0 over 5 plus 32. Well, that's 0 plus 32. That's just 32. And of course, 0 degrees Celsius is the same thing as 32 degrees Fahrenheit. Here's another example. What's f of, say, 37? Well, that's 9 times 37 over 5 plus 32. 9 times 37 is 333 over 5 plus 32. 333 over 5 is 66.6. So 66.6 plus 32 is 98.6. And indeed, 37 degrees Celsius is the same thing as 98.6 degrees Fahrenheit. So this function takes in something in Celsius and spits out something in Fahrenheit. Unit conversion is an example of a function, but hardly the coolest example. This is a much cooler example from the real world. What is this thing? Well, this thing here is a microcontroller, so a very small computer, and it's attached to a couple light-emitting diodes, LEDs. With a name like light-emitting diode, you might think that they light up, and they could. But in this circuit, I'm using the light-emitting diodes in reverse. I'm using them as light sensors. This one happens to be a red one, this one happens to be a green one. So what this circuit does is let me detect how much red and green light is falling on these sensors. The other end is a USB cable, and it plugs into my computer so I can record the results. Data that I gathered from the real world using the microcontroller. It's really two different functions, a function for the red LED and a function for the green LED. Along the x-axis, I've plotted the number of seconds that have elapsed since June 5th, 2012 at 6:03 p.m. And on the y-axis, I'm plotting the number of clock cycles it took to discharge the LED. So what does the red function do? Its input is a number of seconds that have elapsed since this particular moment in time. Its output is how many clock cycles it takes at that particular moment in time to discharge the red LED. Now, this thing was sitting in my windowsill, right? And the sun was rising. And as the sun rises, there's more light shining on the sensors, which means fewer clock cycles are necessary to discharge the LED. And you can see that in this graph. Right? The red function is decreasing as the sun rises. There's tons more examples of functions coming from the real world. Here's one, human population. It's a function. The input is a year. The output is the number of people alive during that year. If you want to see this function, just take a look at Wikipedia and the article on population growth. There's a graph of that function. Along the x-axis is years, and along the y-axis is the human population. And as long as we're searching the internet, here's another example of a real-world function. It's a function I'll call f of n, and I'll be defined by the rule f of n equals the number of Google hits when we search for the number n. Let's try it out. Let's figure out some values of this function, like f of 188. So I plug 188 into Google, and I find that there's about 1.08 billion hits. So the function at 188 is about a billion. Right? The input is 188, and the output of this function is the number of Google hits. Let's try about 4 times 188. That's 752. And if I search for that, there's 308 million hits. Right? So f, the function, at 752 is about 300 million. Now, if we're persistent, we can plug in lots of numbers and make a really nice looking chart like this. Now you do this for hundreds of numbers. Right? You type them into Google, you see how many Google hits you get, and you can plot them. Right? It's a function, so you can plot the graph of the function. Along the x-axis is the number that I typed into Google. On the y-axis is the millions of Google hits that I get. And when you look at the graph of this function, it's not random. There's real structure here. Right? The function's decreasing. Right? Larger values give smaller outputs because there's fewer web pages that talk about really large numbers than about popular small numbers. But even more dramatically, when you plot this on this special log-log graph paper, the graph looks like it's sitting near a straight line. I mean, that's really amazing when you think about it. I mean, this is some sort of pattern that's just hidden in the number of pages that talk about numbers. I mean, why? Where is this coming from, right? It's a function from the real world. Input is a number, the output is a number. We want to understand that function. Calculus is part of the toolkit for analyzing problems like this. So we've seen what functions do. They take their input and they transform it into some output. And we've even got this sort of mental image now, this metaphor of a machine, a conveyor belt that's transforming the input into the output. We've seen how to build a lot of new functions using algebra or, say, composing two functions. And we've thought about some real-world examples. Now, we're going to be thinking more about functions for the rest of the term. But if you've got questions right now, I encourage you to contact me as soon as possible. And I encourage you to get started on the homework right away. Good luck.